Okay, today we are going to talk about unsupervised learning. If you remember, but before starting the course, if you have any question about previous topics and courses or anything, is there any question? Okay. So today we are going to talk about unsupervised learning. If you remember the general picture of machine learning, we said that we have three general big classes in machine learning, including supervised learning that so far we were studying, including regression, classification. They were supervised, and it means that we had some data as samples, and based on those data as samples, we had labels. So, for example, we have thousands of pictures. We have labels per each picture that this is cat, this is dog, this is car inside. So these classes of works, studies and algorithms that we developed were supervised learning. On the other hand, we said that we have another class that is called unsupervised learning. In unsupervised learning, we say that we don't have any labels of data anymore. Let's say we have a bunch of data, and we want to do some stuff with these, but we don't have any label what to do. Today, we want to see what kind of techniques do we have, what kind of classes of applications do we have for those, and we will see the most practical way to deal with this. So as third group that we said we don't talk about it in machine learning is reinforcement learning as third class of algorithms that we have. That in reinforcement learning, we have interactive agent that interacts in the environment and learns from try and error. So supervised learning, we have data and labels. Unsupervised learning, we have data, we don't have labels. In reinforcement learning, we don't have data at all. We just want to have agent that tries in the environment, does interaction and learns something. So these were general perspective of whole machine learning figure. But of course, I need to mention again that we have the machine learning is too huge. We have many algorithms inside. Just if we look at supervised learning algorithms or unsupervised learning, or new technologies that from next week we will start it, deep learning techniques. So too diverse. But what we are learning in machine learning, we are learning the most basic important concepts that you, with knowing those, you can easily understand any advanced algorithm that later you want to also learn. So we are knowing all the concepts, all the underlying structure. Of course, we are introducing some powerful techniques too, but we are making everything easy for you to understand. For example, evaluate, understand the concepts, how to deal with, how to solve different problems, how to select the features, and etc. So now, today, let's dive in unsupervised learning, and let's first define it and see what is going on. If we want to have a look at outline of this chapter, first of all, I will quickly introduce the concept of the unsupervised learning. Then we talk about the applications of the unsupervised learning. Then we talk about the most practical algorithms for unsupervised learning. They are simple to understand, simple to implement, but very practical. K-means and K-medoid algorithms that are pretty similar also. Then afterward, we will talk about performance metrics. We will see that if we apply unsupervised learning technique, can we use previous metrics, and what else we have as metrics over here. For example, we have within cluster sum of square WCSS metric that we will see. We will see the silhouette score. We will see Davies-Bouldin index. And finally, we talk about the choosing optimal number of clusters for problem that we have. So in this chapter, you're supposed to learn the basic concepts of the unsupervised learning and metrics to evaluate. So now, let's start to answering what is the unsupervised learning. As I mentioned at the beginning, we have algorithms that try to deal with some data that we don't have any label for that. So we don't say, like, we have lots of patients, for example, we don't know they have heart attack chance or they don't have. We have lots of people features, like all of us in class. We don't have any label for example, each of you. Then we want to see, do we have an algorithm, if I give you all students' features to my algorithm, like can be exam scores, can be based on your height, can be based on your weight, can be based on whatever, without saying you are girl, you are boy, without saying you are your features, nothing. Can my algorithm do something with it? So this is the objective of unsupervised learning. In order to achieve this, what we're supposed to do, what algorithm is supposed to do, it's supposed to extract patterns of the data to understand it. In addition to patterns, it's supposed to extract structures of data to be able to give us something meaningful. And also, most importantly, relationships between data. So when we have lots of data given to our algorithm, we need to consider these and kind of the technique that we have should try to extract these features, these important characteristics for us from the data. So in brief, we can say the main objective is to extract useful information from the data without prior knowledge or assumption about data. We don't want to say anything about the data to our technique and or our algorithm. So now let's have a look what kind of techniques can we have for unsupervised learning techniques. First class, we have basically three general classes. One of the most common one is the clustering. What is the clustering? I told you in supervised learning, when we want to group the data, we are doing classification. And we introduce lots of classification algorithms. But on the other hand, if we want to do similar thing, if we have data and we want to split it, we call it clustering. So here we want to cluster the data with grouping. When you hear clustering, you must always think about unsupervised learning. When you are hearing classification, you must think about supervised learning. There we have label, here we don't have label. So this chapter is focusing on clustering, that is trying to group the similar shapes of data into clusters, not classes anymore. We call it clusters. For example, we have K-means and a couple of algorithms for this class. The second application domain is dimensionality reduction. That it means that we can use unsupervised learning to reduce the dimension of data. For example, you have a data that each data can have 100 features, 500 features as the vectors that we were talking, like age is one vector, weight is one vector, the salary is another vector, and we can add these features to our data. So dimensionally reduction is to reduce the dimension of data. That is very common in image processing and reducing the dimension of the image that we have. So also today I will show you one example that we can also use kind of these techniques to trick to use dimensional reduction of the, for example, image. We will see. Formally, if I want to define for you to reduce number of the features or independent variables in a data set while keeping important information of the data also. That is important. If you want to reduce the dimension, if you lose important information, that's useless then. What we want to do, then we can manually remove it. The objective is to keep the information somehow. We have also a couple of famous algorithms to do this. For example, PCA, LDA, and we have many different techniques in these classes that we can run. On the other hand, the third most common classes for unsupervised learning, we can say anomaly detection. Anomaly detection is to identify data that diverge significantly from main data that we have, or kind of outliers, or kind of noises. So, for example, you have millions of data that all are like spread it here, but suddenly one is here, one is here, one is here. But 98% is over here. That shows that these are most likely are wrong data, or wrong estimation, or wrong labels, whatever they are. So we don't have label here actually, but they are wrong, basically. So especially in image processing, in robotics application, like your robot has LiDAR scanner, you scan the environment, like I'm scanning the environment, and that's wall, right? All the 3D point clouds supposed to be not farther than that wall. But suddenly you see in your data that some of the data are infinity, or like 10 meters away. But there is a wall, it's impossible that your scanner can scan it. So those are outliers. So that we can use unsupervised learning to have anomaly detection in order to reduce this complexity over here. And you can think now, you can have hierarchy of algorithms from unsupervised learning with using these techniques over here in order to remove the anomaly or outliers, then apply, for example, supervised learning or other techniques in order to much more accurately classify the data. Here also we have some techniques that are mostly based on deep learning techniques, for example, or neural network. For example, variational autoencoders or GANs are in this class. As much as we have time in this semester, also we will try to talk about all those techniques too. Okay, clear? Any question? Now we want to focus on what is the clustering and talk about different techniques of clustering. So as we mentioned, we want to group similar samples together. We want to give lots of data to our algorithm without saying any enable, without giving any information. Then we want to say, okay, give me some underlying structure. Can you give me? We want to ask the question from algorithm. What the algorithm is supposed to do, of course, algorithm needs to find similarities or dissimilarities of the samples in order to be able to give us some information. For example, for these points, over here, the similarity is the location, like the position of the points, that we can say, okay, all of these are together, right? Over here, I can assume that these are in one class, and if I put another group here, then I can say, okay, these looking like another not class, another cluster, another group. So by looking at this data, I can give you those information, right? We want to, so how can I say that? By looking at similarity and dissimilarity. So here we say, same as unsupervised learning algorithms, the objective we want is to find underlying structure or patterns that I explained over there for you. So finally, in unsupervised learning, we want to partition the data into clusters or groups that uses these features as similar or dissimilar. Now, let's have a look. What kind of different types of clustering algorithms are existing? First of all, we said that in unsupervised learning, we have three important applications, 1, 2, 3. Anomaly detection, clustering. And here we want to focus on clustering different algorithms. The first one is partitioning-based clustering that tries to partition the data. Like we say, okay, we have K clusters, and we know how many clusters we want, and our algorithm is supposed to give us, for example, I asked my algorithm, so these data should be in 2 clusters. Then my algorithm partitions the data for me for 2 clusters. The third group over here is density-based clustering techniques. So for partitioning, we have K-means, K-medoids that today we will talk about. But in density-based clustering, what is happening? We want to group the samples based on density of the feature space this time. Instead of, for example, using the metrics of the distance that we will use in the first group. We have different techniques also to do this. For example, DBS scan or optics can do that for us. That works based on the density. As third group, so partitioning, density, we have hierarchical clustering. That in hierarchical clustering, what is happening? We try to make a hierarchy of the nested clusters. Usually what is happening, you say, okay, all my data is in one cluster, then I want to split it to the new clusters and assign the groups to different clusters, or we have like to the number of data, whole of these as clusters, then try to reduce the number of clusters. So I can say I'm a, like if you consider yourself, including me as data, and we can say each one of us is a cluster, is a group, then let's find who is similar to me, who is similar to him, who is similar to she, then try to include the other people. That works in series of the hierarchical clustering, and also we have different algorithms. For example, agglomerative clustering, and we have divisive clustering that are 2 famous techniques to be used in hierarchical clustering techniques. So now we want to focus on partitioning. That are also the concepts. If we learn one, the concepts are similar, just the techniques details are a little bit different, that we can learn those much faster too. So partitioning-based clusterings, K-means. K-means is similar to concept that we've had in KNN, K nearest neighbor. But those are totally different techniques. In K nearest neighbor, we had labeled data, but here we don't have labeled data. But and let's see what it's going to do. It is popular clustering algorithm that is unsupervised and tries to group the data to a specific number of clusters. Same objectives as unsupervised learning that I explained to you. It uses similarity of the features. So now you should think that, okay, we kind of need to write some equations, some objective function in order to find similarity of the data for my algorithm also. And the idea is to iteratively assign examples to the nearest centroid and update the centroids. What is the centroid? Centroid in clustering techniques, unsupervised learning techniques means that we want to have a cluster head. We want to say, so if we want to split this data into 2 clusters, we need to choose some cluster heads or choose some data, features of data that represents the features that I want as clusters. For example, if I have feature x1 and x2, that it is like in range of 0 to 100, this one, for example, 1 minus 200 to for example 2000, whatever the range is, the centroid means that per this x1 and x2, I want to have some value. But the point is, in the range of 0 to 100, you have maybe like 2000, like 500 data that has some random values between these. For example, you have a value like 10 and 2000, 1050, and many data like this. But centroid can have any value in range of possible range for data that I can have. But most importantly, centroid determines the cluster head for me. That is kind of reference. We will see visually soon what it clearly is. So directly I'm going to explain the steps of the k-means, and then we will solve an example for you that you clearly understand. What we have as steps, we initialize k-centroids. Initialize k-centroids usually randomly. It means that I want to say, okay, this data over here should be supposed to be in 2 clusters. So I need to choose 2 centroids. Those 2 centroids, if these are my range of value, are random value between this and this. I choose 2 random values as my centroids that wherever can be on those planes. Can be, for example, randomly one here, randomly another here, for example. Second step says assign each example to nearest centroid. Now, those data over there should be assigned these centroids. We will see next slide in detail. Just now, let's see the steps. As third step, we want to update the centroids. We should update the centroid's location in this simple example in order to put them somewhere that represents my data clusters in proper way. I need to update its location. We will see how. Then as fourth step, simply I repeat these 2 steps. Just assign it again, then update it. Assign it and update. Now, let's one by one see how that's happening visually. If my remote works. First step, initialize k-centroids. It means that choose k random values per each features that you have. Here we have 2 features because let me also complete it, or independent values that here we can say, so this is x1, this is x2, only 2. You may have 100s of that dimension that even we cannot plot. Doesn't matter, we choose per each value 1 random value over there. Let's say this is our data set. This data set shows the age and shows monthly income. And you can consider this is, for example, United States dollars, but a little bit rich guys. So when you are young, your wage is low. When you get older, your salary is higher, monthly salary. So this is data that we have. But if you see now, we don't give any label. Nothing, we just have data, age and monthly salary. We want to now give this to our unsupervised learning technique and ask, can you give me some useful information from this data? So you can look yourself. Can you understand something from this data, very simple data? In unsupervised learning, we want to see how we can do that. Now, as first step, of the k-means algorithm, what we're supposed to do, initialize k centroids. So let's consider that we have k equal to 3. I am developer. I'm exactly saying that I want this data to be clustered, to be grouped into 3 different groups. I say it at the beginning. So what is happening? Randomly 3 values are chosen for me. Totally random. These could be anywhere. 3 random points for me. Clear? So after choosing random points, let's see what we do. In second step, assign each example to the nearest centroid. Now we need to calculate a metric to say how this feature is close to other feature. Here and also commonly used for the k-means or similar algorithms is Euclidean distance, or Manhattan distance can be too. Euclidean, but is more common to be used. So that I can measure the distance from this point to each one of these data points and assign them to the closest one. So if I want to visualize it, it looks like this. Each one of the centroids that I chosen, I measure the data points, all of the data points distances, for example, this one over here, to each these 3 centroids, and see which one is more closer to that data point. Then I assign this data point to the closest one. Here, in this case, this is closer. This is more far, of course. Or this data point is closer to this centroid instead of this. Or this one also is closer to this instead of these 2. So for all the data I have, I assign it to nearest centroid. Clear? Now we did second step. If we want to visualize with color, we can say, okay, now we have a cluster with this green. We have a cluster with these purples and reds, after assigning each one of them. But now, of course, we should do something to improve it. This is like we didn't do just pick 3 random cluster, the centroids, and just assign the data. We kind of should make it more meaningful. What we do, we move to next step as updating the centroids. For updating the centroids, the most common way is calculate the average or mean of the assigned samples. How? We say, okay, we had this data and the centroids. Now, for example, for these green ones, look, can I get the mean? Yes, of course I can do. If I get the mean, what will happen? So I will have a point somewhere around here, center of the data, right? For the red one, the same. And for this purple one, the same. If I do that, then what happens? I can update the centroid. So that this centroid for green one moves to there, moves to here. That the other ones also move to more center part of the data. But the point is, so before, maybe it is better to, before looking at that figure, if I get the mean and calculate the mean, so we have the centroid, centroid, after that I can redo the assigning all the data points to this new update, so that if we do that, then we have this. It means that again I assign data points to closest centroid, so that you see that some of these points that already were green here, now they are not belonging to this centroid anymore. They moved from this to other one. So they instead chosen to be under group of this centroid instead of that centroid. Now, even in second iteration, if you look, this makes sense, right? We have something a little bit more meaningful. Looks like a little bit structured. based on the age, based on the monthly salary. So we can say these guys are high, these guys are medium, these guys are low. But this is not enough. Of course, we need to continue this. So what we do, we repeat steps 2 to 3. And for how long? For when we terminate these steps, we have two conditions usually. First of all, no change in the centroid happens. So the centroid that you have is not changing anymore. The coordinates that it has is steady after iterations, or the maximum number of iterations is happening. Why we have both? Because maybe we have jumping problem in centroid. It's moving a little bit and coming back, moving a little bit and coming back. That's possible. Because of that, we also need to have maximum number of iterations to stop it in some certain points. So if we continue, they repeat these steps. What's happening? It looks like this. We continue one more time. Then what is happening? You see that this centroid moved a little bit higher. This also moved a little bit higher. The red is almost at the same point. We continue. Again, this one moved much more higher. If you compare to here, it is much more higher. And this is at iteration 4 with k equal to 3. Then we continue again. Let's move up to convergence of this to finish these steps. Iteration 5. Iteration 6 is still this purple one keep going up, you can see. Iteration 8 and iteration 9 that almost is stopping over here. Now, look what happened. We applied unsupervised learning technique, very simple, very easy to understand and easy to implement also. And it gave me 3 clusters of data that as I mentioned, like you can now say that these guys are rich guys. These guys are mid-level guys, and these guys are poor guys, for example. I didn't do any labeling, I didn't do anything, but I extracted very meaningful data for me. Now you can say, okay, new data comes, is it rich or is it poor? You can do something like KNN, assign it to one of these clusters, and say, is it poor, rich, or mid-level person? Any question? Of course, this example is very simple. The data sample that we have is for age, monthly salary simple, but you can use it for very complicated applications that can do and extract some from more complicated data that even you don't understand, more meaningful data for you. Now, let's move to a second algorithm that is pretty similar, just we have one critical difference. And we add lots of advantages based on that also. Second algorithm is K-medoid algorithm. K-medoid algorithm, let me go by slides, says, we say it is a variant of the K-means clustering, and it also does the clustering the data to the specific number of clusters that we have, that we already say how many we want. And the key differences is that K-medoid uses the medoids instead of centroids. What does it mean? It means that, look at the data here that I drawn for you. Let me make it a little bit, of course we need those. Okay, just removing that. Look at the data. The initial random centroids that I chosen couldn't be better somehow. Why they should be centered in somewhere nowhere that we don't have any data? Instead, could we choose one of these data as centroid? Yes, we could. And if we do that, instead of centroid, we call it medoid. We say, okay, why you choose somewhere nowhere as data and random value? Just choose one of these as center and call it medoid. So, but the point is, every iteration that you run in the code, also you cannot do again move it to somewhere random in middle. For example, here you cannot move it here. Then also we should move it. If the mean is here, we should assign one of the closest points to that and say, okay, this is the, for example, medoid, not the point that is here, similar to centroid. You may ask if they are equal, we just randomly choose one, exactly equal distance as metric. So K-medoid algorithm, the key difference is that we want to change centroid to medoid. And after getting the average, the most closest data to average data point will be medoid, as I explained on the whiteboard over there for you. All the other steps are the same. We don't change anything anymore. So we say with K-medoids, if you want to see an example of the initialization, should be clear that if I run it for k-means, again can be somewhere random. But if I run it for K-medoids, we are choosing one of the data points that we have. Then that would be much more convenient. Now let's compare. Okay, we saw two simple techniques. Do you think which one is better? Say what?
Depends on how many the data is.
How many the data is? Why?
K-medoid needs a lot more data.
No.
No.
There is no need for more data, but you're very close.
So it depends the k-means initialization.
Depends on what?
Of the first random points of k-means.
That's also one reason, yeah. The initialization can be in these two sensitive. Another? Any other? There is one more important one. Computationally expensive is which one? K-medoid. Because you add one more step of finding which one should be the medoid for you. So that each one, after getting the average, you should find the closest one, right? And finding the closest one, if you have 1 million, then you should calculate 1 million distances, right? Because you have no idea, you should calculate the distances to see which one is too close to this red centroid here to assign it to one of the points as medoid. So that's the another one. But let's see all one by one. Advantage or pros of the K-means it is simple and computationally efficient than K-medoids actually, because one of the challenges of K-means also is very robust technique, is very useful. One of the techniques, one of the also challenges over here that is can be computationally expensive in comparison to other techniques. Widely used and well known, K-means is very well known. Also, you can use it in hierarchy with other algorithms. It's very useful to boost the speed of the other techniques. What does it mean? For example, in one study, I've used it for boosting the task allocation. For example, let's say we want to clean the area over here, and we have 5 people. Then which task who should do? You should allocate which task who should do. The general idea is that if this person is trying to work here, is try to all tasks, better for him to do all the tasks over here instead of doing one task here, one task at the end of class, and come back here, go there, right? is like based on the locations, better to say if you have a robot, this robot should work on this table, this robot should work on this table, that robot, right? And which algorithm can do this? K-means, unsupervised learning. Maybe you say that's simple, I know, of course everybody knows, but you should not think about like human, because we are smart and we know it, but the algorithm that you are developing doesn't know. And the environment can be different, the coordination can be different, then you can use it for robot task allocation and say that, okay, if I have hundreds of tasks that distributed in the environment, then based on the energy, the amount of paths that they need to go, then you can have initial kind of task allocation with k-means that can say this robot should work over here. Then we say also k-means works well with continuous values for cluster centers. Why? Because it's clear we had no limitation here. Actually, with k-medoids, we are discretizing based on the data, but here we don't do anything, just like it's continuous, we can put any value over there that we want. What are the disadvantages of the k-means? It is sensitive to initial starting point, because it can be, like, let's say, 3 of these randomly, if we want to both of these are at the same coordinates over here at the initial, randomly. Then maybe your technique starts in local minima and is sensitive to this point over here. But if you look at the data in K-medoids, whatever you do is on one of these ones are more closer to your data, right? Even if it's in outlier, never is like in corner, very, very far corner. Because this data is like, maybe you can consider is like huge dimension, and it's not like this is small that I draw and spread it on the environment, on the scales that we have diversely, so that it will be a little bit more challenging. And because of that, it may stuck in local optima. Cannot work with binary and categorical data because of that continuous value over there. That's also another challenge over there. And second one is also more challenging for handling the outliers for k-means. This is also, you need to think a little bit deep to understand why that's happening. For K-medoids, on the other hand, let's see the advantage. We say it can, first of all, handle categorical data or binary data, because we are choosing medoid 0, 1, 0, 1 and switching between those, and that should not be a big deal for it. It provides better results, because if you get the average, 0 and 1 becomes 0.5, then the algorithm doesn't cover that. You cannot do anything. You unless convert it to K-medoid automatically for a categorical data. Second advantage is provides better results for clustering, usually. So this comes from many tries on different applications, and reports shows that K-medoids generally works better than k-means in terms of performance and the metrics that you can evaluate on the algorithm. On the other hand, also it is more robust to the outlier and noise. So this can be kind of a homework for you, that you can answer the question why. I'm not going to answer it for you now. Why more robust here, K-medoids, why more challenging for outlier? There is very sweet trick over there. Not trick, sweet kind of reason over there. On the other hand, let's have a look at K-medoid disadvantage. We say for large data sets or hard dimensional data can be computationally expensive, because we have one more step, and that one more step to find which is the medoid, Here, you need to find the Euclidean distance of all the data set with this point. And if you have 10 of those clusters, you need to do that 10 times. And that's, of course, more expensive. And it can be more sensitive to choose of the distance metric also. Here we say simply Euclidean distance. In some data set, you need to define something else that says how close these points are together. Then in that case, can be sensitive K-medoids much more, and you need to be more careful. But basically, over 80–90% of the times, Euclidean distance works for most of the cases. Even if you have color, you want to compare color of the image frames, pixels in the image, then the Euclidean distance is still working. I will show you one sample today. So, let me ask you. So what is the common problem of both of these? He read it, I know. I think you read it too, right? Okay, who didn't read it, then answer it. The common problem for both of these? Yeah, if somebody's reading his skill is high, then quickly read. The most biggest problem for both of these is choose of the how many clusters at the beginning. So in this data, I can clearly say that 2 is good because it's clear that 2. If I say 2, I'm in my mind I'm expecting that my unsupervised learning will cluster this data for me similar to this, right? But if you have 10 dimensions, impossible. You cannot see it. Then how you can say that it should be 2, it should be 5, it should be 10? How you can say that? That's the biggest problem of this technique. The biggest challenge of this technique. Is there any solution, do you think? Yes, there is. And today we are going to study it. We will see how we can find it. How we can find proper K for our unsupervised learning technique. Before that, now let's kind of jump back to answer the similar question that we asked for classification algorithms in supervised techniques. We asked there that, can we use the technique for regression or prediction? For example, the techniques that we studied there, and we said, yeah, we can use it in this term. But we want to ask the same question here. Can we use unsupervised learning to run the regression and prediction algorithms techniques? Not algorithms techniques, I corrected. Can we use unsupervised learning to do regression or prediction? Can we? Hugo, you should answer now. Loud. I didn't hear. What else? Who else? Can we use it or no? Ilham, Rifki, Simon. Can we use or no? What do you think? The answer is actually no. And that's, everybody imagine that we can use it, but the correct answer is not 100% no, but is not common to use, and almost no. Because the reason is because here we don't have any labels, anything to check it out what is happening, if it's correct or not. Then based on that, how you want to predict something in future, how you want to do regression. Because of that, it's not common to use unsupervised learning for prediction or regression tasks. So that we can say are typically used for, we are using unsupervised learnings for exploring the data and or reduce the dimensionality. For example, with autoencoders that we design to let the autoencoder decoder learn the idea. Maybe later we can use it to prediction, but directly we cannot use it for predicting data like regression models. So the answer is not. Generally, it is not possible and or suitable for unsupervised learning to do these tasks. But what we can do, then it's useless if we have that problem over there. If we have regression problem or prediction, then unsupervised learning is useless for us. No, it's not. We can use it as pre-processing step for supervised learning. For example, reducing the dimension. If you reduce the dimension, then it's kind of pre-process for your supervised learning. Then you can use it over there in order to perform the task or predict what you want. Any question? Okay. Now, let's answer, first of all, how we can now know that if the performance of our clustering is good or bad. I showed you with K-means how we can cluster the data, right? Now let's answer if that was good or bad, similar to performance metrics. The first question from you again, can we use the techniques that we've learned already with classifications? For example, we learned accuracy, we learned different metrics. We have like 6-7 different metrics. Can we use them over here or no? The answer is supposed to be yes or no. Precision, recall, accuracy, for example, for classification we've studied. Can we use them? Think. Can we use them? Why? Yeah, correct. You should, if you think about that metric, you think, okay, what that metric was doing? That metric was checking with the label everything, right? The ground truth. But we don't have any label here. We don't have any ground truth here. So all the metrics that we've studied previously are useless over here. We cannot use it for unsupervised learning. So what we should do, we should study new metrics for unsupervised learning techniques. But actually the metrics that we are going to study are simpler. Let's see. For example, confusion matrix we cannot draw over here because we don't have label. So if you see a research that it is unsupervised learning, but that guy represents confusion matrix or those metrics, that's totally wrong. You know, it's impossible unless he do something that explains. So we say it's different from metrics that we use in classifications algorithm, as I explained. There are no predefined labels as ground truth to be able to perform those metrics. So that the most common unsupervised learning metrics are, there are many, like more than maybe 6, 7, 10. But the most common ones is, first of all, within cluster sum of squares, WCSS. This is very important metric because we are going to use it to other purposes too. Second is the silhouette score. And the third one is the Davies-Bouldin index. We have much more, but these three are the most common ones. And we will study today to see how they are working. So what we are doing, we did that. We want to see how good it is. First one, WCSS. Let's see how it works. We say we want to measure with this metric, as its name is indicating, it's simple. Sum of the square distances between each cluster center and assigned data points. Imagine it yourself. If you imagine also, you will understand something also seems to be wrong also. Sum of square distances between each cluster center and its assigned data points. Which means that if I have this one here as data point center and this one as data point over here, I want to measure all the distances of these, right? I don't draw all of it. So that it's clear that if I do that, how much lower it is, it indicates better because it is in the center, Because if this is far, if this point goes there, then this point is very far, these are very far. We are expecting this comes to the center. The centroid or medoid comes to the center of data, and this one also is like, we can say maybe exactly, if I, instead of that point, I draw it here, we have same. Maybe. Let's assume we have same. But this metric says it's better to be preferred to be in the center. So that we can write it mathematically. WCSS of the K. What is the K? Number of clusters that I indicate at the beginning. I say, for example, I want 3. We will see how to automatically find it, but now we are studying about metrics. So WCSS 3, for example, equal to sum of the each one of the cluster heads and sum of the distances of the each data point. So each data point that includes in the cluster. So this term over here indicates that the data points or data that included as cluster I. So K is equal to each one of the cluster's data points, the distances between. This is the centroid or medoid of the cluster. It could be both. Mu of the I. The distances, Euclidean distances of these, each one of these points that include in this cluster with the centroid or medoid, and sum of those plus sum of these. This is the metrics of the WCSS. But something is wrong here, kind of. It will be more clear when we are moving to the next step. But the wrong thing is that, it's not completely wrong, but when we are trying to use it in solely, it always tries to always tries to bring it to the center, that if we don't use it in conjunction with other metrics that we have, then kind of, if we want to use it to find best K, then we will be in trouble. That wait for some seconds, it will be visually visible for you. So metric that shows that how we should move to the center, but if we want to report it, usually we report it with other metrics that visually you will see why, especially when we want to find best K, if we use this metric. Okay. Any question? Is it clear? Good. Now, let's talk about the silhouette score. In silhouette score, we say we want to measure how well spreaded each clusters are. So we want to talk about the spread of the clusters. How they well distributed, because maybe these points are very good in the centers, but they are not distributed very well. So it is based on how this is this metric works. We say this is based on average distances between the data points in the same cluster and the average distances between points in different clusters. So we want to say, okay, the spread, not only we should consider in our metric the data points that we have, but also the other ones in the equations that we write. And based on that, we say higher silhouette score indicates better clustering performance. Simply, we can write it like this in this form. This equation indicates for one data point, not whole. So for one data point of silhouette score says that B subtracted by A over max of the A and B. And what is the A and B? The A is the average distance between a point to all points in the same cluster. So like this point to the all points in cluster, this point to the all points in cluster, this point to the all points in cluster. So each one of the points if I choose as A. On the other hand, what is the B? Average distance between a point and all points of the next nearest cluster. So if I choose this, next best cluster, here we have only one other one, is this one. Then average of this point to all these. If I had another cluster somewhere else, then this again would be this one, but if I choose this one would be this one, not that one, because this is next best one, next closest one. So B subtracted by A, next best, subtracted by my own average, over max of the A of B, that this max of A of B is normalization factor. We say which one values is higher, divide this to the higher one, then we have normalized value between -1 and 1. Just normalize it. Now what we should do, of course, this is per each one of the points. If I want to get for whole, I should run it for whole independent points, independent simple data that I have. So silhouette score is only here in this equation defined for one. I didn't write it because it becomes more very complicated equation. Then you just run it for all, just one for loop or sigma of all of it. Any question? Because if I want to write sigma, then I should indicate B of the I and sigma of each one of them, and then say which one is which class. That would be a little bit complicated to understand. Clear? The point is that each point with itself, each point with the next nearest close. For this one, next nearest close is this one. For this one, next nearest close is this one. Maybe for this point, next nearest close is here, but this one, next nearest close is that one. Also, that's possible. And as third metric and last metric that we want to study, we say it measures the average similarity between each cluster and its most similar cluster. And here, in contrast to previous one, with Davies-Bouldin, we say with lower value, we have better clustering performance. And how the equation looks like, let's have a look. We say dB of the K, that K already is given, is equal to average of the 1 over K. It means the average of the sum of the max of this term. What is it? We have R of the I, R of the J. So both of these says the average distance between each point in the cluster I or cluster J, if we consider for this, and the centroid of the cluster. So that if we do this and sum them up, So we want to calculate this term, pretty similar, but what we do is actually, like, we choose one cluster, add it to the other cluster. I choose this cluster, get the average, and next cluster at the same time also I calculate it. Then sum them up. Then I divide it over the distances between centroid of those. That is here, this distance. Oh, I should have drawn straight line. So I get some of these. I get this one. I get this one, average of these. Then divide to this distance, I and j. And do the same thing with this and this one. And get over average of these. And I get the max of those. The max of those that I is not equal to j. Because then it will be same. So if I do that procedure with this equation, we call it the average similarity between each cluster. How similar this is to this, how similar is to that one. So these are three common metrics for unsupervised learning. I think pretty simple ideas and easy to understand. Now, based on those metrics, we have one more thing to answer. How to choose best K now. You can think a little bit yourself. Can we do something? We have metrics. We have clustering algorithm, we know. Then how to choose best K. What can be the best idea? Yeah. Run K times and see which one's performance is better. Very simple. But during time, the scientists have invented very perfect approaches to this. They say, okay, we should have a standard way to do this, and that is standard way that is simple, efficient, and good. What is that? Of course, we can run it, so we need to run the algorithm for each cluster, but we can use elbow point method. There is a technique called elbow point method that say, okay, now let's run one of the metrics, but detect the elbow point and use that metric to determine what is the K, best K. Because also the reason is that we use, one of the reasons is that we try to use such a technique is that if you look at these calculations that I explained to you, the concept is easy, but you are always calculating Euclidean distance between a lot of points, right? The complexity is too high if you every time want to calculate those points. Because of that, we have elbow point method that, let's see how it works. We say, in elbow point method, we first run the metric WCSS, and we run it for each K WCSS, and we check the decrease rate of the WCSS then. And we try to find the value that looks like elbow, because decreasing dramatically, decrease much more higher than the other steps that we have. We should find the decrease, in which point it decreases a lot. Then we choose it as best K for our technique. So it usually, the decrease usually forms a bend, and also here called as elbow, like elbow that is like bending. You see my arm is bending somewhere in decreasing part. We want to find that point, and then choose that based on the WCSS. So what we have here, I've written that we are indicating adding more clusters case. We start from, for example, cluster One is that, of course, is like 1 is useless, 2, 3, 4, 5, 6, 7, 8, and we increase until we don't see significant improvement up to increasing of the k. So what can be the maximum of k? Where we should stop the k with increasing? Is it infinity? So we can cluster this to 2, right? If I increase it, there should be some stop point for k. Where? Maximum distance above point? Yeah, maximum number of points. We cannot have, that doesn't make sense. We have more clusters more than data that we have, right? If we are 20, 30 here in class, we are 30 in class, then we say we have 31 clusters. We invent one new, doesn't make sense. So maximum k is the number of data that we have, if in case that. So here I plotted for you. This plot is exactly the same plot data for the data set that I showed in the class on these slides. So this is number of the clusters, k. You see that I evaluated from 2 to 10. And here, WCSS metric. WCSS metric, you can see that decreases. Why decreases? The point that was here, I told you that there is a tricky point that is a little bit problematic there. Because if you want to use WCSS purely to say, okay, what is the minimum value? Of course, it decreases always, right? If I add more clusters, the average distance gets lower. And the best one is k equal to n. If k equal to n, it means that per each point I have a cluster. Then the distance of the distance with this metric becomes 0. It goes to 0 at the end. That's why I told you that we don't use these to minimize and to find the k. If you do that, then that's like always says k equal to n is 0. Hurrah! Okay, this is first metric that we studied. You see the plot results. This is second metric. Again, this is based on the data that I showed on this slide. Number of clusters, k is 2 to 10. You can see the metric that decreases, and here almost something looks like converge. Here I also indicated here we had a small value better, but here higher value better, and we can understand something that, okay, oh, the 2 was good already. We added more classes for the data set that we had in these slides. It gets worse after 2 even, right? On the other hand, we have the third metric, and in the third metric you can see that also here we wanted to minimize. After 2 it gets worse, right? So from silhouette, Davies-Bouldin, and WCSS, 3 metrics we plotted. Now in these slides we had 3, but let's see if I plot these 2 that shows good values with these metrics for me. It will look like, in these slides, I put 3 as k. I said looks like 3 is good. Rich, medium, poor. But this evaluation tells me, no, that's not good. If you do that, your clustering algorithm performance is worse. 2 is better. And says me, look, I clustered for you with 2 k's and very nice. Poor, rich. And makes sense, right? This is beauty of the unsupervised learning. And what if, for example, I increase to 6 something? The data will look like this. You can see that still meaningful. Clusters are kind of meaningful if I need to for some purposes, but they are very hard to distinguish these 2. The margin is not very clear, you know, especially between these 2 or these 2 lower classes is not very clear to distinguish. Any question? Okay. Now let's let's run the elbow point method that I mentioned to you. Let's see how elbow point works. It's very simple. I want to find the elbow point. What we do, as I told you, we run the WCSS that we show, and we find a significant improvement. How? Looks like this. So this blue one, so I plotted all together to show it, the same results from previous slide. The blue one is the WCSS, the metric that the elbow point algorithm works on it. And if you look at here, this starting point, the decrease amount is higher than the other ones. All of them are decreasing, right? From 2 to 3, 3 to 4, 4 to 5, all are decreasing. But the amount of decrease is maximum where in the 2 to 3. Then 2 determines best case for me with elbow point method. In coding, you just can get the argmax of the decrease, simply. Create a for loop, calculate the elbow point for each, calculate the WCSS metric for case, and get the argmax of the decrease. Then you can see that 2 to 3 is decreasing, then 2 is the elbow point, that's it. To prove it, to see that it's correct, then we can plot the other metrics. We studied 2 other metrics, and 2 other metrics also prove that for us. Both of them shows that in 2, this should have been minimum, this should have been maximum, shows that in 2, it is perfect. So we don't need even run those others if in case that we need other metrics, because those are computationally complex to find the K, then if your data set is big, takes too long, then you can simply run WCSS. That is also, meanwhile that you're running K-means, you can plug it in, because always you're calculating the distance, right? At the end stage of the calculation of K-means clustering, or K-medoid clustering, at the end iteration, you have calculated the distances already. You have it also. Then you can use it as WCSS over there, then also plot it at the end stage, then find quickly elbow point, then find the best K for each one that you are running. Clear? Any question? And that's again the 2 that shows it is the best. So always we are talking about, for understanding, better simple understanding, we are talking about simple data, as you see over there. But what if we want to, as SVM I told you is very common to use in image processing, very advanced classifications. Here also, can we use these simple algorithms for image processing and image? Yes, we can, for example, use it for image segmentation. How? K-means can be used for image segmentation. So if we want to say, okay, let's have an image, and we want to apply unsupervised learning based on K-means on only color. So you have an image, each pixel has position, right? So let's say positions are not important as feature for me, only colors. I want to run K-means or K-medoids based on only colors to cluster. Can I do that? Yes, you can. I gave this image as input, run K-medoids, K-means based on K equal to 2, then output will be look like this. What are these colors indications? You can see that it's kind of black and white, and these are average color of the each clusters. So maybe you have 100 classes, I get the average, and the average color indicated here, and the average color of the other class. So all these colors of image classified are clustered into 2. And kind of like so I mentioned some note on the slides for readability. What if now not only we want to do the segmentation based on the color, but we want to also consider the pixel positions. as feature, because in the image not only colors is feature but also pixel position can be feature. What if I add that as feature and also weighted it? Then I added some weights for it to make it more significant. You can change the weight of the how much color is important, how much position is important, for example. Then we have something like this. You can see that I gave this image as input. I gave k equal to 3, and you can see that this area, and this area, and look at the image. This is brighter, the average of brighter part, the more red part, and this is like the ground. And here you can see it's more grayish. So if you try different ones, you will see very interesting results with unsupervised learning. This unsupervised learning tells me what? Tells me this image, there are 3 main colors, and this brighter color is the right up corner, this reddish color are on the left corner, and this brownish color down right corner. Without labeling, without anything. If you run the based on color only on this image, what will happen? It will look like that. K equal to 3 again. So it means that the colors that we have here, like red ones, gets closer to color that that is in that cluster and get replaced by average of that. And you can see that what happened over there. Look, we removed the background. My unsupervised learning kind of removed the background over here, is very white. And here, give me just only with 3 colors almost same image for me. I just plotted 3 different values here. If you change a little bit values, you will see many interesting things that is happening. Many useful things that is happening with simple technique of the unsupervised learning. So for today you have a practice. You need to write k-means without using library for giving data, to apply elbow point method, to understand the concept. The idea is that, but I will show you how to implement with library. I have without library, I can show you that too. I did it many times, but for practice, to make sure you understand the concept, you should do it one time. And as assignment, you can apply the k-means algorithm for image segmentation, something similar that I did, based on color and position, and apply elbow method to see, for example, what is I didn't do anything, just I put k3. Give this something like this image to your algorithm and ask what is the best number of clusters for this image that I can have. Then you see that what is the best k over there and what output looks like. Then you think that is it smart, is it useful or bad for clustering technique in unsupervised algorithm. So what we've today studied, if I want to summarize, we understood the concept of unsupervised learning. We introduced the applications of the unsupervised learning in 3 different ways. And we discussed 2 of the k-means and K-medoids algorithm. Then what we did, we introduced the performance metrics, and we saw how elbow method can use this performance metric to indicate how many clusters I should have. So that's it from the slides.